anytime your m is not equal to 0, then you have a complex function. And chemists in particular don't like complex functions. They're hard to imagine. Okay, so we'd like to replace those functions in your eigenbases, in the set of eigenfunctions. We'd like to replace those with real wave functions. In other words, functions that when you plug in x, y, r, theta, and phi, you'll get a real number. Okay, and so it turns out that if you can take linear combinations of functions that have the same L and absolute value of m, and you can get real functions. For example, let's say y1, 1 and y1, negative 1. So this is L equals 1, m equals 1. And this is L equals 1, m equals negative 1. Okay? So the absolute value of m for these two functions are the same. Okay? If you take this particular linear combination given here, what will happen? Let's see. Let's work it out. All right. So this is 1 over square root of 2. What's y1, 1? We have the list here. So here you have a function of theta times e to the I phi, right? So I'm just going to say a function of theta times e to the I phi. What's y1, negative 1? This is the function right here. The same function of theta. It's not this exactly the same. This one is negative and this one is positive, right? So that's going to be, I'm going to call this negative, the first one, okay? I'm going to put a negative sign in front of it. Plus, in this case, f of theta e to the negative I phi. You see what I'm doing here? I'm just going to call this, f of theta, this part that depends on theta, and this part I'm going to call this negative f of theta, because if you look at these two expressions, they're the same. It's 1/2 square root of 3 over 2 pi sine theta. Okay? So what happens now? If I took that combination, what can I do at this point? I can factor out f of theta, right? So this becomes, so this is plus, right? And that's minus, right? Okay, minus, and that's plus. So I factor out f of theta. What do I get? Okay, let me factor out negative f of theta instead. So if I factor out negative f of theta over square, so that's over square root of 2. What do I have left inside? I phi minus e to the negative I phi, right? But what is that? It's minus f of theta over square root of 2. What's e to the I phi? Minus e to the negative I phi. You've seen that lots of times already. Sorry? 1/2, 1 over 2i sine theta, right? Okay, this is cosine of phi. Cosine phi plus I sine phi minus cosine phi minus I sine phi. So I sine phi cancels out. Oops. No. What happened? What happened here? Minus minus is plus. I'm sorry, they don't cancel. It's the cosine that cancels, right? So this will stay. That becomes 2i sine phi. It's the cosine that cancels. So that gives me negative f of theta over square root of 2. That's 2i sine phi. Okay, that's an imaginary function. There's an I there. I don't like that I. right? So what should I do? If I don't like the I multiply it instead by multiplying it by 1 over square root of 2. I multiply it by I over square root of 2. Okay. Or is something wrong with my sign somewhere? Oh, I'm sorry. Okay, sorry. Made a mistake. Okay. This is, there's a minus right here. Okay. There's a minus right here, so that's going to be minus, right? This is y11 over here with a minus. And then y1 negative 1 over here doesn't have a minus, but you're subtracting the 2. So that's a minus. Okay, so if I factor out negative f of theta, so that becomes a plus right there. Okay, so that's a plus. Okay, I did intend for sine to cancel out. All right, so that's a plus. So your I sine phi does cancel out, so you'll be left with cosine phi. Let me rewrite this. So this is going to be cosine phi plus I sine phi plus cosine phi minus I sine phi. Okay. So this, I had this one right. This should be 1, not I. All right. So I sine phi cancels out. That gives me down here 2 cosine phi. Right? And so you can see the whole thing is now a real function. There's no I in the function at all. Okay. Now this is usually called y1x. If you notice, we took two linear combinations, a linear combination of two functions that have different m's, right? One is +1, the other one's -1. So even though this is an eigenfunction of the Hamiltonian operator, it no longer has a definite m, right? So as we'll see, as we've seen earlier when we talked about the particle in a ring, the m value has to do with the angular momentum. Okay, so this is still going to be, so we can't specify an m anymore, so I'm just going to put x there. Okay, and the reason it's called x is because cosine phi, remember what cosine, definition of cosine phi was? X is r sine theta cosine phi, the definition of spherical polar coordinates. So sine theta cosine phi is x over r. Okay, and if you'll notice in your expression right here, you have a sine theta, and so that in your f of theta. So in this particular expression, you're going to have a sine theta cosine phi term, so that's going to be x over r. You can replace that by x over r. Okay, and just as a look ahead, this is what we actually do to get what we call the 2px orbital for hydrogen. Okay, so when we had when you learn about your orbitals for hydrogen in freshman chemistry, you have px, py, pz, right? Now m equals +1 and m equals -1. Okay, those are totally different functions from px and py. It's when you take this particular linear combination of +1 and -1 that gives you what you call the px orbital. So this is actually the spherical harmonic, okay, for a px orbital of hydrogen. Right? All right. So you can do the same thing with this particular linear combination. If you do I over square root of 2, y1, 1 minus plus y1 negative 1, you'll find that you'll have a term that will just be dependent on sine phi. So you'll have a function of theta, okay, times sine phi. And we call this y1. Why? Because you'll see this expression in your final expression. You'll see a term that says sine theta sine phi, and that is just equal to y over r. Okay, so that would be the spherical harmonic that goes along with your p sub y orbitals, the ones that you encountered earlier in freshman chemistry. Okay, so if you want to visualize these real wave functions, this is what they look like.